So I need to give you a resistive value so we can calculate this load current, don't I?
Yes, sir.
So I'm going to make one up. Practice. Practice. I'm going to call this resistor. I'm going to say it's 1.5 ohms. We have enough information to calculate load current. Answer.
4.05.
Or 4.05 milliamps. That's what we're trying to regulate. Does that sound right?
Yes, sir.
Okay. That's the constant current, nearly constant current we're trying to regulate. Regulation process, we need to pick it up. Series, shunt. I told you, if you know series and shunt, you can do voltage feedback. And you can also do this, can't you?
Yes, sir.
Because this series voltage regulator, the arrows for the line in this circuit are the same. When the load changes, it's like the shunt voltage regulator arrows. They're inverse. See what I'm doing to help you out here?
Yes, sir.
I'm trying to help you out. So when the line increases, once again, I total's affected, isn't it?
Yes,
sir.
I total's affected. So I don't want that current to increase, do I?
Yes, sir.
So how do we go about keeping that relatively constant?
Decrease.
More resistors current is going to decrease.
Look here, this top part is pretty much locked in, isn't it?
Yes, sir.
Because I've got the Zener and I've got R1. R1's voltage drop isn't going to change much, is it?
Yes, sir.
So basically, you're dealing with like the bottom half of the circuit. So if I have an increase in current, is VR2 and the base voltage the same thing?
Yes, sir.
So if there's an increase in VR2 due to an increase in overall current in the circuit, I have what type of transistor?
NPN.
PNP. So if I apply a large potential on the base, which is N-type material, what's the transistor going to tend to do? It's going to conduct less. And look, there's the proof right there. The base voltage increased a little bit, didn't it?
Yes, sir.
So it's going to conduct less. Naturally, the VCE is going to do what?
Increase.
Increase. Because I don't want this current to do this, do I?
No, sir.
I want it to stay relatively constant, but if I increase the line, total current goes up, doesn't it?
Yes, sir.
So the circuit automatically senses that, and based on how it's configured in this Zener diode here, because it's keeping this top half of the circuit relatively constant, well, R2 is the guy in this circuit that's, for the line side at least, increase or decrease its potential across on the base. It's going to control what Q1 does. You make it conduct more or less. I like that.
Good.
That's how this one works. Line voltage decreases. I total is going to want to do what? Well, not want to. It's going to decrease. So the circuit has to compensate for that. It's the opposite. Now, if I go like this, VR2, voltage drop's going to be less now, isn't it?
Yes, sir.
So now less potential on N-type material is going to cause that depletion region to do what? Forward bias, and transistor will conduct more because I need more current to the load to maintain that constant, don't I?
Yes, sir.
See how I'm running my mouth about just da-da-da-da-da-da, and we really haven't crunched any numbers or anything. We're just talking about it. Does this make sense?
Yes, sir.
And if it's not, to some of you, if it's not, this is the third time I'm talking about this stuff. The third time I'm spending a lot of time talking about these things. If you're not down with Ohm's Law and Kirchhoff and this aero analysis stuff, or well, the theory, then you better get with somebody that knows what they're doing and talking about and get a different take or spin on this. Shunt. Well, shunt for the load changing. Shunt voltage regulator, how the arrows go. They're inverse. So I'm giving you hints to help you out here. When the load changes, just treat the arrow analysis like their shunt voltage regulator. I'm giving you the damn answers. Helping you out. So, load increase. The load increases. Now, what did I give you? I gave you a formula for this one, didn't I? What did I tell you to do to this side for the load? Look at your notes. Somebody wrote it down. For the load side, what did I tell you to do? You better check your, don't give me that crap. You don't understand the question. See that? Some of you don't write the damn notes down that I give you during the lessons. That's why some of you are sitting there like a bunch of rocks, don't know what the hell's going on. Because you don't even pay attention during the damn lesson itself. So you're sitting there like, I don't know what's going on. This is the third time I'm giving you the same information. This is supposed to be a review. Not reteaching the damn annex. Which is basically what I do anyway. Some of you need to wake the hell up and frickin' study tonight. Because now I'm getting irritated. What the hell's the formula that I gave you for this? Somebody's got it. What is it?
VR1 plus BCE plus VRL.
That's what I told you to do for this side. I'm giving you the answers. I'm giving you the help. It's all here. I'm explaining how it works. This is just Kirchhoff stuff. That's BEO1. For the load side, do this. Because the line voltage isn't going to change, is it, this time?
No,
It's going to stay the same. What did I say about VR1? Yes, exactly, because it's in parallel with the Zener. Guess what I can do with that little arrow there? I just do it like that. Doesn't that make sense?
Yes, sir.
R1 is in parallel with CR1. Look, it's right there. Well, gee, it's damn near equal to what the Zener is. It's just 0.6 volts less. That's it. So now, load increases. What is there a potential to do here for the output of, or what's the load voltage going to do? I basically have the same current. I'm increasing the potential. Mr. Brown, what's going on?
When the load increases, that's going to cause the voltage drop across the load to increase. So to compensate for that, the BC is going to have to decrease and make the transistor conduct more to maintain a constant current.
Do you actually get it, or are you just looking at your notes?
No, actually.
Okay, that's good. Good. That's it. Remember, this is a current regulator. If I make this load larger, what's going to actually change? The load voltage. So think about the load voltage. Because essentially, when we're dealing with the load, the I total's the same, isn't it?
Yes, sir.
If I put a larger load in here, well, obviously some of that current's going to kind of go over this way, isn't it?
Yes, sir.
It is. So how this circuit compensates, hey, the load voltage, hey, it's essentially the same current. Load voltage is going to go up, VCE goes down. This is how you can look at this, because VR1, essentially constant. VCE and VRL equal source, doesn't it?
Yes, sir.
So if this happens, the VCE must do this to compensate and equal the same line, because the line voltage isn't being screwed with this time. Transistor is going to conduct a little bit more to be just a little bit more current to the load, so it remains relatively constant. VCE decreases, it's still inverse. The load goes down. Load goes down or decreases. Load voltage, VCE has to
Increase.
So if VCE increases, it's going to conduct a little bit less. This side of the circuit, this side, just Kirchhoff it. Use this. Kirchhoff it. Or, bottom line, if you're not down with any of this theory that I just went over for the third time today, just memorize the damn arrows.